The multiverse has moved from the realm of theoretical physics to become a star of popular culture. Films like Everything Everywhere All at Once or the Spider-Man and Doctor Strange sagas portray it not through rigorous science, but with a philosophical twist, envisioning a web of realities where every choice spawns a new world. Physicist Sean Carroll explains that while Hollywood plays with imaginative versions, alternate selves you can meet or fight, quantum physics and cosmology propose much stricter versions of the multiverse. Why does this idea fascinate us so much? Perhaps because it lets us imagine other possible lives, ones where we didn't make certain mistakes, where things went better. That longing for another path reveals our deep discomfort with uncertainty and regret. In a way, it offers comfort. Maybe, in another universe, we ended up exactly where we wanted to be. But Carroll reminds us that physicists didn't dream up the multiverse out of fantasy. It wasn't born in science fiction, but emerged as a natural consequence of following the clues left by the observable cosmos. The multiverse isn't a fantasy, but a serious implication of theories like cosmic inflation and the many worlds interpretation of quantum mechanics. These frameworks don't just explain our universe, they predict others. Universes with different particles, different laws, maybe even no humans at all. In cosmology, those other universes could be so far away that we'll never reach them. But quantum mechanics introduces an even more radical idea. Each time a measurement occurs, all possible outcomes happen, but in separate parallel worlds. This astonishing idea, developed by Hugh Everett in the 1950s, suggests that every choice, every path not taken, still unfolds elsewhere. Reality doesn't split. It was already multiple to begin with. A parallel reality isn't just fantasy. It's a logical outcome if we accept the deepest rules of quantum theory. Still, it raises a compelling question. Is every possible world truly real? Carroll clarifies, science doesn't claim that anything imaginable must occur. What happens is constrained by the equations of reality. For instance, an electron will never turn into a proton. The laws of physics forbid it. But it can spin clockwise or anti-clockwise. And according to many worlds, both outcomes become real in different universes. In cosmology, the multiverse helps explain why our universe is so uniform. The inflationary theory says that early on, a violent expansion smoothed things out. But that inflation doesn't stop everywhere. It continues in pockets, spawning universes with entirely different conditions. Beyond this lie purely philosophical versions of the multiverse, places where every conceivable scenario has its own realm. Though many remain skeptical they exist at all. Even if we can't observe these other universes directly, the possibility reshapes how we understand our place in the cosmos. It invites us to think bigger, to question what's truly real, and to embrace the mystery. Because in contemplating the multiverse, we're not just looking outward, we're also looking inward, wondering what it means to be one version of ourselves among an infinite sea of possibilities. And perhaps that's part of the allure. The multiverse invites us not only to ponder physics, but to reflect on choice, chance, and identity. Could another version of you be listening to this video, making a different decision right now? The question of why we should trust the many worlds interpretation is answered most simply by its elegant clarity. Physicist Sean Carroll argues that this theory is not a fanciful add-on, but the direct solution to a core conundrum of quantum mechanics. The measurement problem. In stark contrast to classical physics, which deals in definite positions and velocities, quantum theory only offers probabilities. so what actually transpires when an observation is made. The Copenhagen interpretation tried to isolate the observer from the quantum system. Sean Carroll emphasizes that Hugh Everett had the insight to treat the observer as part of the quantum framework. Consequently, when an electron is measured, there is no unique outcome. Both results occur, but in distinct universes. Schrödinger's equation naturally accommodates these worlds without discarding them. Rejecting them introduces needless complexity. Embracing them simply follows what the mathematical equations dictate. Another pressing question follows: how many worlds truly exist? Sean Carroll acknowledges that we do not know. There may be infinitely many, or perhaps a number so stupendously large, populated even more densely than real numbers between 0 and 1. Even with infinitely many worlds, we can still assign meaningful probabilities. Some universes would be more typical than others. If quantum branching is continuous, then the universe is splitting every instant. For example, around 5,000 radioactive decays occur per second within an average human body. Each decay could trigger a branch. One universe where it happens, another where it does not. If every split doubles reality, that amounts to 2 to the power of 50,000 new universes per second. What is the total number? Sean Carroll speculates figures on the order of 10 to the power of 10 to the power of 100, a quantity beyond human comprehension. But one thing is certain: the multiverse is not sparse, it is astonishingly prolific. Who are we within such an eternity of worlds? Sean Carroll invites us to reconsider personal identity. If grappling with continuity of self over years is complex, what about versions of ourselves diverging at each quantum event? When you observed the electron spinning anti-clockwise and another version of you saw it spin clockwise, are they still you? The answer is nuanced yet clear. They are distinct persons. Much like identical twins sharing an origin but diverging in life, each version of you branching into a new universe should be regarded as a separate individual, each with their own existence and dignity. This is not mere fantasy, it is an expansion of consciousness. To conclude, the many worlds interpretation asks us to see ourselves not as solitary beings, but as part of an awe-inspiring branching tapestry of consciousness across the multiverse. We might never meet those alternate selves, but their existence invites us to honor the profound mystery at the heart of reality. Let it serve as a mirror, reflecting not only who we are, but who we might become. Do our decisions create other universes? Sean Carroll warns, this is a natural human tendency, our instinct to position ourselves at the center of every unfolding story. Yet, from a physicist's vantage point, the situation is unequivocal. In the cosmological multiverse, alternate universes lie so far beyond reach that none of our actions here can ever influence them. This misconception arises from our need to find purpose and meaning, even when confronted with incomprehensibly vast realities. At the quantum scale, reality splits repeatedly, but not because of deliberate decisions. Rather, it is driven by subatomic events that unfold according to the laws of quantum mechanics. We do not choose when the universe branches. We are instead carried along by its inherent randomness. Sean Carroll assures us, however, that this does not diminish our value. We inhabit a world governed by universal laws. While we cannot track the position of every atom in our bodies, we remain moral agents at our scale. Our choices retain weight and consequence. The multiverse, rather than absolving responsibility, highlights it. No matter how many other you exist across realities, the decisions you make here and now are yours alone. But why is the multiverse so compelling? Sean Carroll believes we exist in an era where imagining alternate lives has become routine, even habit-forming. Modern technology, far from simply connecting us, also invites us to explore worlds that aren't real. We flick through dating profiles, dream about homes on property apps without any intent to act. These are glimpses into parallel possibilities. Such everyday windows constitute a casual psychological multiverse. Sean Carroll points out that the human mind is embodied, not merely software. Envisioning ourselves in alternate scenarios influences how we think, plan, and feel. Imagining different paths can spark actual change in our current lives. And yet, there remains a boundary. Significant choices are irreversible. Time travel is not possible. The multiverse may offer insight, support, or consolation, but it cannot rewrite our personal stories. Films like Everything Everywhere, All at Once vividly illustrate this duality. Evelyn may appear her worst self, yet she discovers meaning and redemption. The moral resonates deeply. Though there may be countless versions of ourselves, only the one we are now can shape its destiny. Sean Carroll emphasizes another profound truth. Causal influence extends only into the future. What has happened remains fixed. What will happen depends on what we do today. The multiverse acts as a mirror, reflecting our deepest hopes, regrets, and aspirations, helping us reconcile past choices while imagining a fuller future. Perhaps that is the true power of the multiverse. It not only intrigues and entertains, it awakens. And if the multiverse truly mirrors our inner lives, perhaps it's more than theoretical physics. It's also emotional truth. It invites us to reflect, not just on what reality is, but what it could be. When we look into this infinite mosaic, we aren't merely observing the universe. We're glimpsing ourselves, fragmented, evolving, and forever capable of choosing what comes next. What is time? Sean Carroll offers a direct perspective. Time is not as mysterious as it seems. We use it every day without hesitation. We say "see you at 7," and no one panics over the abstract nature of time. In everyday life, time is merely a label we attach to events to distinguish one from another. The real puzzle is not what time is, but why it seems to flow in a single direction. Why do we remember the past but not the future? Why do we age? Why can't we change what has already happened? St. Augustine reflected on this enigma centuries ago. He claimed he understood time, until someone asked him to explain it. And he was right. What feels natural is in truth profoundly perplexing. Science has made significant advances since then, yet our intuition often fails to align with physics. It is difficult to imagine a universe in which the past and future are not defined as opposing directions. Yet that is precisely the reality dictated by fundamental laws. They impose no direction. The arrow of time we experience isn't derived from the theories themselves, but from the history of the universe. We are creatures within a cosmic narrative that began with a remarkably ordered start, an anomaly that changed everything. The idea of a time arrow is deeply embedded in our human experience. However, as Carroll explains, the fundamental laws of physics do not distinguish between past and future. Newton, Einstein, and other towering theoreticians formulated equations that apply equally well in either temporal direction. On the microscopic level, time holds no preference for one direction over the other. So why do we perceive time as flowing forwards? The answer lies in context. Just as objects on Earth fall downward due to gravity, even though down is not specified in universal laws, time also appears directional because we exist in the aftermath of a defining event. the Big Bang. That event not only marked the birth of space, but also created an initial state of exceptionally low entropy, which has been increasing ever since. Entropy is the measure of disorder. There are far more disordered arrangements than ordered ones. Therefore, in the absence of intervention, everything naturally tends toward greater chaos. Time acquires its direction because the universe began in an extraordinarily ordered state and has continued to move toward increasing disorder. That is why eggs break and never spontaneously reform. It is not magic, it is physics. And all of it traces back to that original cosmic moment. The arrow of time is not a universal law, but a consequence of our specific thermal environment. It is a local illusion, born from the unlikely order ushered in by the Big Bang. The story of entropy begins with steam engines. During the Industrial Revolution, engineers encountered an inconvenient truth. Useful energy is always lost. There was no way to build a perfectly efficient engine. This constant loss was soon interpreted as a reflection of a natural law, the second law of thermodynamics. According to this law, entropy, disorder, increases over time. And so, the idea took hold that the universe naturally tends towards more chaotic states. But why does this happen? In the late 19th century, Ludwig Boltzmann proposed a radical explanation. If we accept that matter is made of atoms, then entropy increases statistically. There are simply far more ways for atoms to be disordered than to be neatly arranged. However, Boltzmann's theory explains only why entropy increases as time moves forward, not why it started out so low in the first place. That's where the so-called past hypothesis comes in. Formulated and named by philosopher David Albert, it suggests that the universe began in a state of extraordinarily low entropy. Why? We don't know. It's not a conclusion, it's an assumption. But it's a necessary one if we're to explain why we perceive time to have a direction. This initial state, the early universe's remarkable order, remains one of cosmology's greatest mysteries. Why did the universe begin in such an improbable, finely tuned condition? There's no definitive answer. Some physicists accept it as a brute fact. Others speculate about unknown laws that might explain this origin. What we do know is that without this extraordinary beginning, the history we know, evolution, memory, decisions, simply wouldn't be possible. It's as though the universe was finely tuned, not for life, but for time itself. And within that time, life found a way. Understanding this hypothesis is not merely theoretical. It's an invitation to rethink our relationship with time, not as victims of a relentless flow, but as conscious participants in a cosmic narrative shaped by initial order. This asymmetry isn't only physical, it's psychological. We feel time passing because the information in our brains always flows from the past. Our memories, our experiences, our expectations, all face forward because everything we know comes from a more ordered past. Carroll illustrates this with a simple example. When you touch a surface, you expect a certain temperature. If it's different, you revise your understanding of the world. This constant comparison between what was, what is, and what could be creates our sense of time flowing. And so, even though the fundamental laws make no distinction between yesterday and tomorrow, our experience clearly does. Not because time demands it, but because our consciousness arises in a universe where disorder steadily increases. In a sense, we are not merely observers of time. We are its storytellers. The unfolding of entropy doesn't just shape galaxies or stars. It shapes our dreams, our hopes, our decisions. Through this cosmic drift toward disorder, we find the very clarity to define what matters most. That is the paradox of entropy. From chaos, we forge meaning. In this cosmic tale of entropy and time, perhaps our greatest gift is awareness itself. The ability to witness the arrow of time, to remember, to act, and to imagine what comes next. Contrary to what many assume, life does not battle entropy. Sean Carroll suggests that life is only possible because entropy increases. Without it, the universe would remain static. No history, no memory, no change. The universe began in a simple, low entropy state and will ultimately end in simplicity, but maximal disorder. It is in the journey between these extremes that complex structures like us emerge. During this cosmic transit, form, information, and motion arise. We are fleeting but astonishing systems exploiting this disequilibrium. A brief oasis of complexity between two eternities of cosmic simplicity. Without the steady rise of disorder, nothing interesting, no life, no consciousness, would ever have occurred. The second law of thermodynamics may seem discouraging. Everything tends toward disorder, but Sean Carroll explains this doesn't prohibit complexity. The Earth is not a closed system. It absorbs energy from the sun and dissipates it into space. This exchange allows pockets of local order to increase, even as global entropy grows. Complexity does not violate entropy. It flourishes because of it. Living beings ride this wave of entropy. They don't fight it. Every breath, every heartbeat, every thought taps into this flowing energy. We are proof that pockets of order can form, persist, and even thrive amidst increasing chaos. From the tiniest microbe to complex ecosystems, life demonstrates how nature uses entropy not as an enemy, but as a source of structure, adaptation, and purpose. Before Darwin, William Paley argued that complexity implied design. If we find a pocket watch on the beach, we naturally assume it was purposefully crafted because its parts work together so seamlessly. Paley then applied this reasoning to living organisms, stating that such intricate structures could only arise from a divine designer, God. This reasoning formed a cornerstone of the teleological argument for design in nature. Throughout the 1800s, scientists refined the tension between cosmic order and increasing disorder, cementing the idea that entropy inevitably rises. The second law tells us that systems drift toward disorder because there are vastly more disordered states than ordered ones. As a consequence, a closed universe inevitably moves toward maximum entropy. At that final state, equilibrium rules. No stars shine, no life exists, no meaningful activity occurs. A cold, homogeneous, chaotic universe. This is the so-called heat death of the universe. High or low entropy states may differ in disorder, but share simplicity. True complexity thrives at intermediate entropy, neither perfectly ordered nor totally chaotic. Consider cream swirling into coffee. Sometimes it forms elaborate fractals, at other times blends smoothly. The central question remains, does physics naturally favor paths rich in complexity? And was life's emergence inevitable, or a highly unlikely cosmic accident? We still don't know. The universe can be understood in layers. On the everyday level, we see people, chairs, and animals. For physics, everything is composed of elementary particles. Are both perspectives valid? Absolutely. Belief in protons and electrons does not negate the reality of human beings. This layered coexistence of descriptions is called emergence. Complex systems that arise from simple components, yet are best understood at a higher level, with incomplete information and their own principles. In contemplating these layers of reality, from quantum particles to human experience, we recognize that our very existence reflects the extraordinary journey of the cosmos. We are not mere spectators of complexity, but active participants in the unfolding tapestry of time and entropy. Our choices, our awareness, and our curiosity are all emergent features riding the wave of cosmic evolution. Embrace this humility and wonder. Within the grand play of fundamental laws, we find meaning, creativity, and responsibility. Complexity is not accidental. It is the cosmos knowing itself through us. After Isaac Newton formulated classical physics, Pierre-Simon Laplace grasped its deterministic implications. He imagined a perfect intellect, Laplace's demon, capable of knowing every position and momentum in the universe, predicting the future and reconstructing the past. This vivid thought experiment raises profound questions. If one knew everything, would there be room for surprise or choice? But Laplace recognized that humans are not all-knowing demons. Our knowledge remains partial, our mental capacity bounded. Yet, that does not prevent us from acting effectively. In fact, our lack of total information is precisely what makes genuine decision-making possible. We make sensible predictions, we adapt, we choose. Humans function as agents, not passive cogs. We enact our own intentions, observe outcomes, respond to feedback, a continuous cycle. This capacity to envision different possible futures and intentionally select among them gives our lives coherence, moral relevance, and a profound sense of agency. Therefore, while the universe obeys physical laws, our human-level perspective and ability to decide infuse those laws with meaning. We are not puppets, but participants. Conversations around free will often stall in semantic quagmires. A more fruitful approach is to clarify what we mean. Two prominent perspectives stand out: libertarian free will, endorsed by thinkers such as Immanuel Kant, contends that humans transcend physics, capable of spontaneous, law-breaking choice. The dominant scientific stance acknowledges that, to be sure, we are bound by natural laws, but that does not negate our meaning or responsibility. Sean Carroll embraces the second, known as compatibilism. It proposes that being a physical entity governed by physics does not preclude talking about ourselves as genuine decision makers. This dual perspective hinges on the idea of emergence. Different layers of description describe the same reality. On the macro scale, we use mental and moral categories that make sense at our level, without contradicting the atomic level view. Determinism is a philosophical concept separate from the free will discussion. Even in a quantum universe, where chance plays a role, there remains structure and law. Compatibilism accepts both deterministic and indeterministic physics, but affirms that at the human scale, concepts like choice and moral responsibility remain valid and meaningful. At our scale, we speak of emotions, wants, values. At the cellular or atomic level, none of these exist. Confusing these levels leads to a category error. Both perspectives are equally legitimate. They simply apply to different descriptive layers. When we choose between a blue shirt and a red one, we do so naturally, without needing atomic calculations. Our emergent reality supports such discussions, and they do not conflict with fundamental physics. The main criticism of compatibilism is its supposed lack of clarity. How neatly can one divide agent-level language from particle-level description? Compatibilists answer that we should use agent-based language wherever it remains practical and explanatory. Even as AI systems come to mimic decision-making, we can discern their limitations. Simulative cleverness is not the same as genuine understanding or moral agency. Our humanity resides not in perfection, but in acting amidst partial knowledge. Within this uncertainty stretches the space where real choices with ethical weight and personal significance take place. It is our imperfection, our embeddedness in a vast, law-abiding universe, that gives our decisions depth. The compatibilist view thus affirms that meaning, purpose, moral responsibility, and personal growth can coexist with scientific explanation, not in spite of it. Ultimately, understanding ourselves through both scientific and humanistic lenses is not a contradiction, it's a necessity. We are physical beings, yes, but also storytellers, thinkers, and moral agents. To ignore either perspective is to reduce the richness of human experience. The compatibilist framework doesn't just allow room for meaning, it insists that meaning is born precisely from our limitations, our context, and our capacity to reflect and decide. Perhaps that is what makes us truly remarkable. Not that we define nature's laws, but that we create significance within them. And that concludes our video. If you enjoyed the content as much as we did, don't forget to subscribe so you don't miss a single episode. Leave a comment below. We'd love to hear your feedback and suggestions for future videos. And don't forget to turn on notifications to stay up to date with all our updates. Thanks for being part of our community. See you in the next video.